In part 3, we will tackle mathematics and physics from an epistemological point of view. So what's the how can, because most of our viewers can say, yeah, mathematics is mathematics, physics is physics. So how can we relate epistemology with these domains? Yeah, go ahead, Dr. Nasser.
Yeah, so actually, epistemology is a form of meta tool with which you can see the overview of what you are doing, which is always good. You should never go and do things without having an overview of what you are doing, actually. So in math, we have always certain phenomenon, and most of the mathematicians, as I said, consider math to be a reflection of reality which is existing. And this was at least until the 20th century, until the mid of the 20th century, many people really thought that math is reflecting the phenomena which are really existing in the reality. And this type of philosophy in itself, where the phenomenon is a math or logical truth, and this truth exists independent of the mind, this is called the correspondence theory of truth. Of course, we are going to discuss that this is not accepted by many scientists today. We know now, because of the limits of our formal systems, that this cannot be valid. So you had at least originally math where you have a phenomenon, and then you reduce this phenomenon into your consciousness, and in your consciousness you have logical argumentation, as you see here, deductive arguments. You could also have here inductive arguments. You have a certain language, you have certain terminology of the language, you have certain axioms which provide the basic assumptions about your phenomenon. Of course, all this is reduced. It's not the full phenomenon, but only a reduction of it. So in the same time, I am reducing, but also believing that whatever I reduce really exists in reality. So you have sentences in L, which are theorems, you have axioms, you have deductive arguments. And in the beginning of the last century, this was all done using the so-called first order logics, which is the first step which was the first step in mathematical logics. It's the first step of formalization, which was invented actually by Frege, and then developed further by many researchers, including Russell and the Vienna Circle and all this. Now, there is a question here. What are the meanings of the language which I choose? So I have sentences in a certain language. I do arguments. The question of the semantics, which we already discussed before, we said that this interplay between language and its semantic is very important. So the meanings of L, if L is a first order language, you find in second order logics. So you have actually a hierarchy of logics, one after the other. One is providing the meaning of the lesser. So second order logics, in second order logics, sentences in second order logics are actually the meanings in first order logics, and so on. This structure of mathematical logics is the structure we know today to be relevant for many areas of research. I have first order logics, I have second order logics, Second order logics provide the semantics for first order logics. I may have third order logics and so on. Now, what makes a language first order? What makes second order? This is a technical discussion, which I don't want to go into, of course, because it's a
It's
little
very
complicated.
complicated enough.
Yeah. So
has to do with,
yeah.
I think this is has to do with the programming and.
No, it has not to do with programming. Has nothing to do with programming. Programming is something different. But let's keep here in mind that we will have always a certain reductionism. Yeah, you have the phenomenon which you are talking about, but you reduce it. In spite of that, you think whatever you reduced is really existing in reality. This is the way mathematicians usually view the world. Yeah. Now, we have here, of course, a big question, because while I can prove the axioms here, these are the axioms, the red ellipses are the axioms. So the axioms of L, it's possible to prove the axioms of L sometimes, not always, but sometimes it's possible to prove the axioms of L within the L prime, within the bigger language. So it's possible to prove sometimes axioms of first order logic in second order logic. But the question is, what about the axioms of second order logics? So you could think that we have third order logic in which you can prove the axioms of second order and so on. So somewhere you have to hypothesize again. So somewhere this proof structure has to stop. You need to somewhere to start from something where you cannot prove. So this is what makes the life of mathematicians actually not very easy, because they know somewhere, even if they make a very big hierarchy of languages one after the other, somewhere they have to start with something which is not proven. Yeah, so they know this, but they accept it, and most of our science lies actually in this realm, second or first, and first order logic more, because first order logic with the first order logics is more easier to compute. It's easier to compute. I'm not saying that it is always computable, but it's easier to compute than second order logics. So this is the view in math. Let's see the view in physics. Now, physics is more advanced epistemologically because it put a line between the phenomenon and whatever is we do
the tangible
about
world. Yeah, the tangible things.
yeah. So here, the phenomenon is a physical object. It exists independent, or it might even not exist independent. Anyhow, whether it exists or doesn't exist independent has nothing to do with what we do here. So it's actually, this is usually called the ontological level. So the level of ontology, the existence of the things per se, has nothing to do with what we do in physics, actually. So we build consistent models only. And this is called coherent theory of truth. And you could also call it critical rationalism. Yeah, so you have a certain phenomenon. You reduce the phenomenon through experiments, of course, because experiments will tackle some properties of the, not all properties, but some properties of the phenomenon. So what do we have in the conscious part? We have again this picture where you get axioms. You have also axioms, of course. So you did a model for your object or for the phenomenon. You have an axiom, but you have also here a very clear line. You know that this is not reflecting truth as it is, because for you there is no truth as it is. Yeah. So physics does not.
So may I ask
accept physics does not accept the idea that there is that truth as it is can be reached by our science. Physics refuses to say that whatever we find in physics is truth as it is. Yeah. So how does it work? The language is math, of course. It takes math as a language. Now we know from the last slide that math itself takes logics. If we take mathematical logics as a basis, so this means that indirectly, physics takes logics as also as a basis. It takes math, means that you describe your models using usually equations. You don't describe it using Aristotelian or mathematical logic assertions, but you use math directly. You form theories, you have terminology, and this is the formal system of modern physics. It is based upon math. It has some axioms. Now the question is, from where do we get the axioms? Of course, all this is objective scientific evidence leading to empirical belief. So whatever in physics is a belief.
Not
It's
knowledge,
not,
exact knowledge.
Yeah, it is not, knowledge is something exact. But what we have is belief. Why? Because the axioms, most of the axioms you are using are actually also beliefs. They are beliefs. They are not knowledge. Like what we said about Newtonian first law, we can say the same about the uncertainty principle in quantum physics and so on. Yeah. So the axioms here maybe is different to whatever we saw with mathematics, that our axioms here, they don't come via proof. For example, uncertainty principle, there is no need even to prove it. You just enough that in your experiment you don't falsify it, as we said, because we have experiments. So we don't if we don't falsify a certain thing, then it becomes like a wall. I tried to falsify something for a long time. It became, and so I tell myself I am incapable of falsification. So this is where the incapability principle comes. For example, they wanted for a long time to know the place and the energy of an electron, for example, of a certain particle. And they tried a lot, and they thought it is
This
only
is in
about
quantum physics, if I'm not mistaken.
Yeah. So somebody came and they failed all the time. They failed. Whenever they found the electron in a place, they lost its energy. Whenever they got its energy, they lost its place. So with time, Heisenberg, especially Heisenberg, came with his uncertainty principle, which says that we are not capable of determining in the same time the place and the energy of the electron. So this is now an axiom. This is now an axiom of modern physics.
So is the incapability
coming from
is a
our
principle
incapability.
in science, per se.
Yes,
And the rule.
incapability. Yeah, incapability is a very important heuristic principle in physics. It's heuristic. When I say heuristic, means practical. It's a practical principle. We discussed before how I get the physical law. Actually, I do this also with normal physical laws. Like I have a certain informed guess, and this informed guess comes out of my experiments. And if I find something which I cannot falsify, there are many things which I was not able to falsify, I was not able to achieve, then I put this as a wall or as a principle, like uncertainty, which we have discussed now. Now, if we look at formal systems of math, physics, and language, here for the first time, I put also language. We'll see why. So the syntax are the formats of first order mathematical logics. Means you have only very few
Dr.
functions.
Nasser, you captivated language with natural science, huh?
No, we'll see. We'll see what. No, this has nothing to do.
Because most of the people saying language is a domain of human.
We'll come to this. We'll come to this.
Yeah.
In this slide. I'll come to this in this slide. So in math, you have the syntax. You have formulas of first order mathematical logics. you use actually very few functions, only 0 and the successor function. You have for the semantics first order models. I will not go in detail to explain what this is, of course. You have axioms, like for example, for the arithmetics we do in school, we have so-called piano axioms. For set theory, we have the Riemann-Frenkel axioms. Axioms are actually a set of rules which you apply on numbers to get other numbers and so on. Now, we use sound deduction rules. We use also refutation. Refutation means that I start with assuming something is false, and then I find a contradiction, or with assuming something is true, and then find a contradiction, which means that I refuted my original assumption. So you use theorems using, you prove the theorems using inference rules. You hypothesize without evidence. As we said, in math, we don't have an experimental body of data.
It's a formal system.
Yeah, so what we do is that we assume some hypothesis. If I don't have a proof for something, then I assume whether negative or positive that this is the thing which is happening. Now, in physics, the syntax are formulas of mathematics, calculus, differential equations, geometric spaces, probability theory, and all this. The semantics are the empirical models of physical phenomena. So we do for the electron a certain empirical model constituting of formulas of math, and we know we give for each notion we use in our formulas a certain semantic. Our axioms and principles are empirically non-falsified. So for example, Newton's first law. So our axioms need to be non-falsified. Of course, I'm not going to build physics on a principle where I can do an experiment which falsifies it. The principle should be not falsified. Inference rules are math operations, and the theorems you use also, you prove the theorems like you do in math using the mathematical operations. Now, the hypothesis on which physics is built are assumptions non-falsified using experiments, and they can be also using the incapability principle. Now, I go now to natural language, and this is coming to your question. For a long time, until before Chomsky, natural language was considered to be non-formalizable. Yeah, of course, I'm speaking from the point of view Western science. So Western science actually looked upon natural language and disregarded it. Yeah, it was not like, for example, if you take the point of view of Frege and Russell and Tarski, even they were really very skeptical, unhappy with natural language, and they considered it to be humanities between quotes.
Yeah, and it's not accurate enough,
and not formalizable. Yeah, until the beginning of the 50s, I think, maybe the end of the 40s, and then until Chomsky. Actually, when Chomsky came, he could show very clearly that even the syntax of natural language follows formal rules. Yeah, and this is very, very important discovery, because this discovery, this is a breakthrough which is the basis for all modern programming languages. So actually, if you think, why are we now using English for programming? Yeah? In the beginning, there were only zeros and ones. Yeah? So what makes you use English to program any machine? Exactly this discovery that at least some aspects of natural language are formalizable. And this is the great Chomsky. Actually, Chomsky is really one of the most important
is the father of the modern linguistics. as
Yeah,
well.
so he is in the same time father of the modern linguistic and of modern programming languages, if you think about it like this, because he discovered some formal properties which are very vital, like regularity, context-free, context-sensitive,
And later
context
on,
sensitive.
we will zero in on this topic in the case of Arabic language later.
Yeah, we will come to this. We'll come to this. But in anyhow, so until Chomsky, when Chomsky showed them that syntax is actually formalizable, there was a big boom. Actually, it was like a revolution started, and it is still going on until now. Of course, there was a big quarrel. What semantics lies behind the syntax of natural language? So Chomsky himself refused, as he told me, because I contacted him to ask him about Arabic. He refused to give logical semantics to natural language sentences. And my recent publication was exactly about this. I can show that he's right, especially for Arabic. Arabic contradicts the idea of semantic models from logics. Means if you do for the Arabic language semantic models in first order or second order, so on, you disturb Arabic semantics actually. Here, but most of them, I mean, Chomsky is one direction, but most of the current linguists, especially computational linguists, they consider semantics to come a little from first order, from logics, and much more from what we call lambda calculus, which is actually more powerful than first order, but it is still a Turing machine, something like a Turing machine, which I will not go further in detail. Very important is now the discussion, what are the boundaries of the formal systems? For math, this was a very big surprise, actually, because they started with the idea, all of them started with the idea, I can do everything with science. Yeah, I can do everything with science. There is no limit. There is no upper boundary.
And this
when
this is the main idea of the Enlightenment, especially in the 19th century as well.
Exactly. So they took this idea. They were very euphoric and very
deterministic,
happy, very happy to go into this endeavor. But by the middle of last century, here comes the first very important boundary by Gödel, Kurt Gödel, the so-called incompleteness theorem, where he showed that any formal system expressive enough to express arithmetics with Peano axioms is either inconsistent or incomplete, i.e., some theorems will always remain unproven. So he showed that even if you take the very basic mathematics which children take in school, when we say arithmetics and Peano axioms, this is what we take in school, multiplication, addition, and so on. Using this very simple axiom of school, you can write some theorems which you cannot prove at all. You are not able to prove using mathematical logics. So he showed that this whole endeavor, this whole trial to put mathematics on a complete and solid foundation, especially complete,
was an illusion.
means complete means that any theorem you can prove using the axioms. This is not possible. So Gödel came, it is year 1935. In the same time, approximately, Skolem is a guy who is at least as important as Gödel, but many people don't know him. He showed that first order predicate logics cannot express some important mathematical concepts adequately. So even if I want to express some concepts like express exactly, I mean, when I say express in this context, mathematics and mathematical logics, I mean to exactly characterize what I mean by finite, what I mean by infinity, and so on. he showed that first order logics cannot express those mathematical concepts adequately. Means as a tool for expressing infinity and finiteness, which are very important concepts in mathematics, of course. You cannot use mathematical logic. So this was another very big blow. Another blow came, I mean, all this shows that mathematical concepts are actually relative to an interpretation, not absolute, which is a very big blow to the idea that they represent some reality. Yeah. So actually, they don't. You cannot. If you are still hanging around with the concept of absolute truth or a reality which I can attain in somehow, then you misunderstood these boundary results. So mathematical concepts are relative to an interpretation, not absolute. The last but not least, algorithmic decidability. Many important math problems are proven to be undecidable. So for the first time in history came someone who says that here is a very legitimate question of science, an open question, which we will never decide. Yani, take care of the difference between we can decide now and we can never decide. So what these results mean is that if we stick to our fundamental mathematical logics as it is now, as done by Frege and all the logicians and so on, we cannot decide some problems even if we take 1,000 years in research. So this was new. This was very new epistemologically, because never before someone said, we have here a boundary of our own language or our own perception. Yeah. For the first time, someone came and said, okay, it's here is if we continue with these axioms of mathematical logics, which are very important for rationality, actually. Many people consider mathematical logics a synonym for rationality. So this is the first time where we can show now that we cannot decide algorithmically many problems. Now, what happened in physics is something similar. In the same time, approximately, they started to change geometric spaces, dimensions, and so on. And they found out when we change these things, scientific evidence changes. All of a sudden, the experiments give me something else. Oh my God, this means that experiments are also not giving the absolute truth. Yeah. If I change if I change only the geometric space, the way I measure things, and then get something completely different, then this means that I never really reflected reality. Yeah. Which actually they by that time they knew. Changing the perspective of measurement also changes scientific evidence. Physical truth is relative, not absolute. Now, this is very important. Uncertainty is a principle, not a mistake. Now, at that time, the people thought that uncertainty is only because we don't get the right instruments and all this. But now there is a more general result. Tarski is a guy who is a logician, mathematical logician, and he is the one who formulated the actual formal system which we use today of mathematical logics. And he investigated formal systems which might not be logical, because not all formal systems are logical systems, but all logical systems are formal systems. Yeah. So logical systems are part of the formal system. Formal system is something more general. So he studied formal systems in general, and he found out that any concept of truth is relative to a set of axioms, not absolute. So we know now that in the moment where we introduce formal systems, and this will be very helpful when we investigate the Islamic background, because we know now that any formal system cannot contain a definition, a correct definition of truth within this formal system. You need to have something bigger to define the truth inside the smaller one. So this is relative to a set of axioms, not absolute, and it cannot be defined within any formal system S, but in a meta level S prime, in which relations in S are objects in S prime.
We can we can reach we can know realities or some relative truth, but we cannot know the truth in absolute.
There is no truth in absolute. For our purposes, of course, in our daily life, we know that there is some truth outside, of course. But science is here saying that it is not concerned with this ontological outside truth. It is concerned only with our faculty of knowing things and believing things. So if we only concentrate on our faculty of believing and knowing things, then it is the truth is only relative to a set of axioms, and it cannot be defined within a formal system S, but it needs a meta level. Yeah. So here I would like to make a reference to fiqh and usul, because also why do we have usul of fiqh? Actually, usul fiqh is the first. I mean, I may be wrong, but I don't think there is any meta science before usul. Usul al-fiqh is this exact meta level. If you take mathematics out of the phrase and put fiqh, you will find that this guy Tarski is
and
actually
it's translated fundamentals of jurisprudence.
Yeah. So actually Tarski has shown for any formal system that, and especially formal system of fiqh. Yeah. So in the formal system of fiqh, you cannot define the truth. You need a meta level for fiqh to decide the truth, and this meta level is already there. It is usul al-fiqh. So actually Tarski has reiterated for the formal system in a very, of course, in a very precise way, what Muslims knew hundreds of years ago, that you need to have a meta level to define the truth before going into the science. So for any science, I need to define the truth within the science. I need a meta level to define it, which is exactly what we have in fiqh. And this is a very good link, actually, because it simplifies our idea around formal system of fiqh. How much time do we have now?
I think we have 2 minutes. Yeah.
Only 2 minutes. I think we can
conclude this part. Yeah.
We can conclude. Yeah. Let us conclude this part because
briefly, because it's a copious data, so we cannot elaborate more, because our audience can understand it and take their time to fathom our stomach.
Yeah. So we are still in the first part, and thank you very much.
You are welcome, sir. But you can so you need to stop here, and in the fourth part we can elaborate more.
Yes. Yeah.
Okay. Thank you so much, Dr. Elnasser, for your precious time. And we will leave it here at the point that we discussed the limitations of science, and we gave examples from math and physics, and how science is not an absolute thing, as some ideologues or scientism claim, that our knowledge is limited, and uncertainty can be in the field of fiqh, and we will discuss in details these issues in the coming parts, God willing. It was an amazing lecture, and copious, I can call it copious, full of details. And God willing, we will do more videos to talk about your project, your main project. All these parts are paving the road to the point.
As I said before, we are trying in this first part, this whole first part, we are trying to get some tools which make our life easier to understand what
the
formal
project.
systems of fiqh are, and our project also at the same time.
Thank you so
Okay?
much, sir,
Thank you.
and see you in the next
Yeah,
part.
thank you.
God willing, inshallah. Thank you so much.
Assalamu alaikum.
Bye.